Good afternoon. As of now, there is no candidate. So let me just wait for another 4 minutes. And then I go about delivering the contents of the day. Okay, well, so welcoming to contact session 12, where we are going to see solving linear programming problems by simplex method using simplex algorithm. Let's see in detail now. Let me share. Already in the last session that we have discussed in detail about the conditions that are to be met for solving an LPP by simplex method, that the given objective function should be of maximization type. Otherwise, it should be made to be of the type. And we have to include slack surplus variables as and when required, depending upon the nature of constraints. Then we have to ensure that the variables are all non-negative. The right-hand side constants in the constraints are all non-negative, and so on. Well, the topics: introduction, the simplex method, what we do by this method, to start with, and what is simplex algorithm, how it gets used in using the method to solve an LPP. Of course, followed by illustrations and exercises. Rather than enumerating all the basic solutions of the LP problem, linear programming problem, as we did in graphical method, the simplex method investigates only a select few of these solutions. So here, unlike in graphical method finding solution, we will not be finding all the basic solutions, in the sense all corner points as we did in the method by graphics. Here we find a select few of the solutions. And here it actually gives a computational detail of the simplex algorithm which is being employed in solving an LPP by simplex method. What is simplex tableau? We are going to enter present in a tabular form which will take care of all the objective function, constraints, basic non-variables, basic and non-basic variables, their coefficients, the constants, and the process that we do. And finally, we get the solution at the end in the right corner of the table itself, after doing required number of iterations. So the simplex method involves doing iterations. So it's an iterative method. What's happening then? So long as you don't get the optimal solution, you need to iterate, and you will stop the moment you reach the optimal solution. So what is the condition that you understand or you come to know that the optimal solution is reached? Is all about the simplex algorithm. The simplex algorithm can be carried out conveniently by representing the given objective function, constraint equalities, basic variables, basic solution, etc. in a tabular form known as simplex tableau or simplex table simply. Consider an LPP in the standard form. So in the last session itself, we have discussed in detail to rewrite the given LPP in the standard form. What is the meaning? Look at maximize Z. Z is the standard reserved notation for the objective function, like your f. Z equal to, you have the linear combination of the decision variables, supposing they are n, with the constants c1 x1 plus c2 x2 plus extra plus cn xn, subject to the constraints, which are nothing but the coefficients of your matrix, isn't it? So a11 x1 plus a12 x2 plus etc plus a1n xn, the conditions would have been less than or equal to b1. If it is less than or equal to b1, you will add the slack variable denoted by s. Being the first one, it is s1 equal to b1. In order to write it in the standard form, the constraint which is an inequality to be made to be an equation, either we add a slack variable or we subtract a surplus variable. If the inequality is less than or equal to, that is already it is short of. So you are making a compensation. You are just adding a slack variable to make it to an equation. In the same fashion, if the constraint is already greater than or equal to, then you will be removing the surplus. You will put minus s, 1 or 2 or 3, depending upon the equations that are there available in the equation. So in the next equation, a21 x1 plus a22 x2 plus extra plus a2n xn plus s2 is equal to bn. So what is the meaning here? In simplex algorithm, the constraint should all be always less than or equal to type. That means you only have to have addition of slack variables s1, s2, etc. Finally, am1 x1 plus xa etc plus amn xn plus sm equal to bm, such that all the variables x1, x2, etc. xn and s1, s2, etc. sm are non-negative, greater than or equal to 0. We find that s1, s2, etc. sm, the slack variables, can be taken as the basic vector capital B. So as you know, we have the column vector capital X, which is vector of unknowns or having components x1, x2, x3, xn, whose values are to be found. So they form the solution. They are the decision variables, isn't it? But the variables that we introduce, which are slack variables here, can be regarded as a vector. Let us say B, because they are going to form, they are going to be called basic variables. Therefore, we use the word letter B. So it serves as a vector so that you have its components, the slack variables. If there are three constraints, you have S1, S2, S3. If there are only two constraints, you have S1, S2. Since you are having M constraints here, it is S1, S2, etc., Sm in the objective function. And the coefficients in the objective function are zeros. Because in the objective function, originally, they are not there. Objective function is, after all, a function involving the decision variables and, of course, the coefficients. So these are introduced by us. Therefore, they are not originally in the objective function at all. Therefore, naturally, if at all you write that they are also present in the objective function as if, then it will become only, for example, C1 x1 plus C2 x2 plus etc. plus Cn xn plus 0 s1 plus 0 s2 plus etc. plus 0 sm. They are not there originally in the function. So their coefficients in the beginning will always be zeros. So we can write CB means coefficients of the components of the basic vector. In the sense, basic vector is nothing but vector having basic variables, which are nothing but the slack variables. So CB is nothing but their coefficients 0, 0, 0, etc. 0. The simplex table representing the initial solution is given below. So we need to initiate. We need to start with an initial solution. Remember, the simplex table is going to serve not only from further fine-tuning it by iterations to get the optimal solution by simplex method. Next, when we are going to solve LPP using big M method, that is some Chom's penalty method, after getting the artificial variable introduced, and that it is after one stage, then we will be, after the initialization, we will be going back to using simplex table. And therefore, the simplex table serves a best tool to solve an LPP, not only just by simplex method, but also by later on big M method and two-phase method, etc. Okay. Now look at table. You have, of course, in the left corner, you can write capital Z, because Z is equal to C1 x1 plus C2 x2 plus etc. plus Cn xn plus 0 s1 plus 0 s2 plus etc. 0 sm. Isn't it? And therefore, what's happening then? Here you can write initially the vectors, the decision variables, and also the slack variables. So x1, x2, x3, etc., xn, then xs, some constant, some common general term, then xn, s1, s2, etc., sm constant. So in the very first row, you write, of course, in here in this table, you can write z as if z equal to c1, x1, etc. But therefore, you can write in the left corner, you can put simply the objective function z. So you will write the variables x1, x2, x3, xn. You will write the slack variables s1, s2, x3, sm as they form the variables in your objective function. Now, in the first column, you write CB, that is coefficients of the basic vector. You write in the second column, B stands for basic vector, that is vector having the components as a basic variables, which are nothing but the slack variables. So you write S1, S2, S3, etc. Some general term SR, etc. SM. Their coefficients are initially 0, 0, 0 in your objective function. Later on, the values may be changing. But anyway, in the final solution finding, they will not be of any use because they were just coming in and then going out. You are also going to see the entry of a non-basic. Therefore, since we are talking about these slack variables, auxiliary variables as basic variables, the decision variables in the question, in the objective function, are being called as non-basic variables. Okay. Therefore, here you write the coefficients of these variables. In the first column, you are writing coefficients of the basic vector components, that is S1, S2, etc. They are basically initially zeros. And here you will be writing the coefficients of these variables C1, C2, C3, etc., CS, etc., Cn. You know very well, where originally the coefficients of the slack variables are 0, 0, 0. The same thing what you have written here will be here also. Okay, and constant. And you know very well, Z objective function will not have any constant in the right hand side. You will only have a linear combination of the variables. Therefore, constant is also 0. So with this background, now come inside the table. So the inside the table, what do you mean by the first row? First row is nothing but the first constraint coefficients. A11, A12, A13, etc. Some A1S, general term, etc. A1N. Now, what is the coefficient of S1 in the first constraint? 1. All other slack variables will have coefficients 0, 0, 0. What is constant? B1. So if you look at the first constraint, you have A11x1 plus A12x2 plus A13x3, etc. plus A1nxn plus S1 equal to B1. Same way, A21, A22, A23, A2s, A2n, 0, and S2 coefficient alone will be there 1. All other coefficients will be 0, and constant is B2. Similarly, if you continue, and finally you have AM1, AM2, etc., AMN, 0, 0, 0, etc., 1, and the constant will be, of course, here it is missing BM. It should be there, BM. Clear? So, what's happening then? You have the constants on the right, initially for the objective function 0, and for all the constraints, the right hand side constants are B1, B2, etc., Bm. And now that we go to the last row of the table that we create, we started with the Z here, and then we had here CB, B, of course, CB is nothing but coefficients of these slack variables, which we write here also. And one thing you can note that in the right hand side of the slack variables, coefficients within the table are nothing but they are forming the unit matrix 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, etc., 0, 0, 1, etc., etc., 0, 0, 1. So suppose you only have 3 constraints. Then in the first constraint, you will have S1 with coefficient 1, no S2, S3. So 1, 0, 0. In the second constraint, 0, 1, 0. In the third constraint, see 1, 0, 0, 0, 1, 0, 0, 0, 1. So you have a unit matrix. So in general, it is a unit matrix. So now finally, we make a calculation, a computation in the last row. And that is Zj minus Cj. Zj minus Cj. Small cj, Zj minus Cj. So what is this Zj? Here it is shown here. Zj, how do you calculate Zj? Is nothing but CB into AJ equal to, of course, according to this initial table, will always be 0 for all j, since CB has the components coefficients 0, 0, etc., 0 in this table. So what do you mean by CB AJ? It is 0 into C1. AJ is nothing but A1 column. Okay, so their coefficients, not C1 actually, 0 into A11. Okay, the constraints. So the columns here, this is A1 column, this is A2 column, this is A3 column. These are all concerned with your coefficients of the constraints. So here you have 0, that is your CB, into A11. A capital A1 is nothing but your A11, 0 into A11 plus 0 into A21 plus 0 into etc. will always be 0 because these coefficients are zeros. So 0, okay, Zj minus Cj, that is 0 in the initial table, it will always be 0. Okay, minus Cj means minus C1. First column, you get minus C. 0 minus C2, minus C2, minus C3, etc., minus Cs, etc., minus Cn. And here, 0 minus 0, 0, 0 minus 0, 0, etc., 0 minus 0, 0. Therefore, in the last row, Zj minus Ej will only have negative of the coefficients of your non-basic variables or decision variables x1, x2, extra, xn, namely minus C1, minus C2, minus C3, etc., minus En. Suppose you have somewhere here negative coefficients, you will have here positive coefficient, the change of sign. And in the right-hand side, since all the coefficients of the slack variables are zeros, you definitely have 0 minus 0, 0 minus 0, etc. will only be 0. And in the constant also the same thing, because the whole thing here Zj is 0, your constant is also here 0. So you will get only 0 minus 0, 0. Because it is 0 into B1 plus 0 into B2 plus 0 into B3 plus 0 into BR, etc., 0 into BM, which is 0 minus constant. You get 0. So this will be standard. In your simplex table, in the initial table, you will have only these are zeros. So you just look at, therefore, the starting solution is, what is S1? Just see S1. S1 value is B1. Okay. And S2 value is B2. S3 value is B3 and so on. Sm value is Bm. That is called a starting solution. And Z not equal to 0, of course, naturally. Because what is Z naught? Initial value of Z, in which the basic, non-basic variables, that is the decision variables, will have the coefficients only zeros. They are being equated to zeros. You will not take C1, C2, etc. Okay, you will take them initially 0. So it is 0x1 plus 0x2 plus etc. plus 0xn. So Z naught, the initial value of Z will always be 0. And Zj is Cb into Aj. It will also be 0 for all j, since Cb has coefficient 0, 0, 0, etc. in this table. Therefore, Zj minus Cj equal to always negative of the coefficients of these coefficients of variable. That is, according to this table, minus Cj in general for all j. And this factor, this Zj minus Cj is called relative cost factor. So these will all be useful for your answering quizzes. Okay, Zj minus Cj is called relative cost factor and is denoted by Cj bar. You can denote it by Cj bar just to have a simple notation or a single notation instead of writing Zj minus Cj. But I would suggest you can write Zj minus Cj itself as it is, because that is available readily in your table. Because you should know, only when you write Zj minus Cj in this fashion, you will be able to do the calculation. Isn't that? Therefore, you can write Zj minus Cj as it is. If at all you want to rewrite which is equal to, we can just put Cj bar. It is not Cj, but it is Cj bar. Some complement of your Z is a Cj, isn't it? Thus, Cj bar in the initial table, Cj bar is minus Cj in the starting table. So Cj bar is minus Cj always, when only in the starting table, initial table. Okay. Now, testing for optimality. Now that we need to test whether the solution that we have has got optimal solution. If not, we need to iterate. And how do you iterate? When will you get the optimal solution? Where will you stop your iteration? Just look at. For that, we have a condition. In the starting table, if all the relative cost factors are non-negative, Cj bar is nothing but Zj minus Cj. Non-negative, you can have 0. it cannot be positive. It can even be zero, but not negative. That's why we use the same non. We don't say positive. We say non-negative means zero is also included. So greater than or equal to zero for all j. Then it is not possible to increase z further. And the current solution itself, sorry, and the current solution itself is the optimal solution. So in the starting table itself, if you have your Cj bar, that is Zj minus Cj, are all greater than or equal to zero, it will not be. It is possible only when you have all your coefficients C1, C2, X are all negative, then Zj minus Cj will become positive. Isn't that? Which is very rare. So if Zj minus Cj are all positive, then you have, if they are all greater than or equal to zero for all j, then it is not possible to increase Z any further, and the current solution itself is the optimal solution. Therefore, for optimality, the condition is that Zj minus Cj must be greater than or equal to zero for all j. That's important. Okay. Suppose there exists some Cj bar. Maybe Z, so you have Z1 minus C1, that is C1 bar. Or Z2 minus, some of them may be zero, some of them may be positive. If there is one, at least one Cj bar less than zero for some j, then select the most negative of them, say Cs bar. If there is only one, okay, you are taking only that. So that column corresponding to that particular Cj bar, which is negative, is called a pivot column. It's called a pivot column. And if it is not there, if you have something more, you have something more, some more than one, then select the most negative of them, say Cs bar. The corresponding column, As. Suppose it is a yes, Cs bar means yes item. So that the corresponding column is denoted by As. It's something like your C1 bar, C2 bar, etc. General CS bar means As. Otherwise, A1 column, A2 column, first column, second column, etc. is called the pivot column, and the corresponding variable non-basic. Which are the variables are called non-basic? The variables that are available in your objective function originally. They are the unknowns whose solutions are found, which will give the maximum value of your Z. They are the decision variables. So that we take it as non-basic vectors. So and the corresponding variable enters the basis. So that particular column, yeah, so against As you have your Xs, isn't it? So that will enter your basis now. Basis means it will come to the basic vectors column, where there are many rows. Which of these S1, S2, etc. will be replaced by that Xs? For that, you need to find pivot row. Their intersection will give you the entry of your non-basic variable into basis, that is becoming basic vector, and that the basic vector already there, like S1, S2 or S3, whatever it is going out, is leaving. Remember, it is not swapping. When X2 is entering here from A2 column, corresponding to say some pivot row, say S2. S2 will not go there. S2 will be leaving. X2 will be entering, but S2 will be leaving. Once and for all, it will be leaving. That's all. It will not go back to that position. It's not swapping between. Okay, right. That's what we mean. So that is very important. Enters a basis and becomes a basic variable. So non-basic variable becomes now a basic variable for the improved solution. Thus, Xs is the entering variable here. Now, to get the pivot row, you have to go for finding ratios. Bi bar AIS. Bi means the constants on the right hand side, B1, B2, etc., Bm. AIS means A11, A12, A21, A31, like that, some general coefficient in your constraint, isn't it? AIS. For all AIS greater than 0, you must divide those coefficients of constraints available in the body of your table corresponding to the constants on the right hand side, the division ratio you are taking. Remember, you should only consider those AIS which are positive. Do not take equal to 0 or less than 0. You take only positive AIS greater than 0 and divide BI by such positive coefficient in the AS, in that pivot column, and choose the minimum ratio. So you may have 2 or 3 values in the ratio column by dividing the constant by the corresponding coefficients. Then let us say here BR by ARS. BR is the constant and ARS is the positive constant by which we have taken. And now, supposing we are having 2, 3 ratios, you choose the minimum ratio. Okay, then the corresponding. So suppose we have taken the minimum ratio obtained in BR divided by ARS. So that row will now become pivot row. So you have pivot column, you have pivot row, and therefore the element ARS. AS column element is your pivot column, AS is your pivot column, and now AR is your pivot row, so that the intersection of these two is given by the element small a suffix rs. ARS is called the pivot element, which indicates that the variable SR. So corresponding to this intersection of pivot row and pivot column, you have in the table on the left hand side in the second row a basic variable SR. That is S1, S2, S3, etc. Here generally SR, that leaves the basis to which XS is coming, X suffix S, maybe X1 or X2, depending upon the nature, and becomes non-basic in the improved solution. So SR leaves the basis and becomes non-basic, means it will not go to the place of XS. XS will be there as it is. It will only be leaving out. Okay, that is very important. Since XS becomes a basic variable, the pivot column should have all the elements equal to 0 except the pivot element, which should become unity. What's the meaning? Again, we are going to do the row elementary operations. That is, the pivot element can be any number, any integer, positive or negative. You have to divide by that number so as to make it 1. So the pivot element should be made to be 1. Okay, this you already seen in solving system of equations by Gauss elimination method by partial pivoting, isn't it? So make the pivot element to be unity. When pivot element is made 1 unity, other element should be made zeros by elementary row operations. In order to obtain this, we make elementary row operations, which we know very well. This process is called iteration. This process is called iteration. In the modified table, XB contains XS as a basic variable in place of S4, SR, and CB contains CS in place of 0. Okay. So what will happen naturally? When XS is coming into the basic variable column, its corresponding coefficient will be there, not 0, because SR has already left. So CB contains CS in place of 0. Thus an improved solution is obtained. Once again, we find Zj minus Cj. So one table is now there. It is the improved solution. So now we find again Zj minus Cj and examine whether the current solution is optimal. If there is possibility of improving further, proceed to find out the entering variable and leaving variable and modify that table. This process is repeated until we obtain the optimal table in which Zj minus Cj, or in short Cj bar, is greater than or equal to 0 for all j, and the corresponding solution is the required optimal solution. Okay, now we have seen theoretically the simplex table, how it is formed, and what are the things the simplex algorithm is all about, and then how we go about doing iteration after iteration until we reach the optimal solution. So the condition for getting the optimal solution is that Zj minus Cj must be greater than or equal to 0 for all j. You can have 0, you can have positive value, but not negative. If it is true for all j, then that is the optimal solution. So where do you get the optimal solution? How do you find out? And therefore, how do you get the value of Z? That is ultimately where we are interested in, getting the maximum value of Z. And also the values of the decision variables that are available in that objective function, say x1, x2, x3, x4, depending upon the nature of the question. And there will be values of the slack variable, that is basic variables, corresponding to them in under B, basic vectors in the constant column. For example, you have S2. All those basic vectors will not be left, will not be leaving out. Some of them may be available, and some of the in the row elementary operations, you may get some constants. You may write down their answer, but they are not going to be helpful in getting your maximum value of Z, because they are not appearing originally in the objective function at all. So they are just tools to improve upon. Okay. Right. Now, just see that. Solve. This is very important. Solve by simplex method. Maximize Z equal to 3x1 plus 2x2, subject to the constraints, minus 2x1 plus x2 less than or equal to 1, x1 less than or equal to 2, x1 plus x2 less than or equal to 3, x1 comma x2 greater than or equal to 0. Okay. Remember, this also I have already made it clear in the last session, and that the number of decision variables available in the objective function need not be the same number of constraints that you are having. For example, here you have two decision variables only, x1 and x2, but you have three constraints: minus 2x1 plus x2 less than or equal to 1, x1 less than or equal to 2, x1 plus x2 less than or equal to 3. These are the three constraints. And the last one will always be talking about the non-negativity of the decision variables, and also the slack variables, of course. Okay, right. Now solution. So before we start preparing the initial table or starting table, that is the simplex table, we need to rewrite the given LPP in the standard form. The standard form of LPP is maximize Z equal to 3x1 plus 2x2 subject to the constraints, minus 2x1. Look at, you must ensure that the inequalities are of less than or equal to 10. Okay, it is already there in the given problem. So we can just go about rewriting the given LPP in the standard form. So minus 2x1. So the coefficient of x1 can be negative. So that's not a problem. Minus 2x1 plus x2. Since it is less than or equal to, and that should be of the type, plus s1 equal to 1. x1 less than or equal to 2. So x1 plus, don't write again as s1, because see, the 1, 2 are not anything reserved for slack and surplus. And as far as simplex, it is only surplus, sorry, slack variable. So in the first equation, when you write s1, in the second equation, it is s2, because it's another variable, plus s2 equal to 2. Third constraint, x1 plus x2 plus s3 equal to 3. Well, the last one, don't make it as an equation. Don't add any slack variables. Okay. So the last equation will always be giving out the general criterion that it speaks about the non-basic and basic, or decision variables and the slack variables in the easy understanding should all be non-negative. That non-negativity should be spelled out as the last condition or last the constraint. x1, x2, s1, s2, s3 greater than or equal to 0 is the standard form of the LPP which is to be solved, which is to be optimized maximum. Look at the table. As I just mentioned, which was not originally in the simplex table, which was missing. So you can put above the CB and B because he said has got everything, this decision variables and slack variables. And here in particular, first column, the coefficients of the basic vectors, which are the slack variables, right? Okay. So first you fill the first row, x1 is it equal to, isn't it? You only fill the variables, x1, x2, s1, s2, s3, slack variables, which are not originally in Z, should also be written there. Of course, you will write the coefficients to be 0 each, and also the constant, right? So now you go for making the under Z 2 columns. The second column, of course, you put B, which will have basic vectors, which are nothing but the slack variables, s1, s2, s3. In this problem, there are only 3 slack variables, and their coefficients are basically CB means coefficients of basic vectors 0, 0, 0. These are standard. Now coming to this second row, you now write the coefficients of x1, x2, s1, s2, s3. x1, x2 in the problem, if you just go back, three x1 plus 2x2. So the coefficients are 3, 2, isn't it? So 3, 2, s1, s2, s3 is coefficients are 0, constant. Naturally, there is no constant on the right hand side. Is that equal to? So 0. It is standard. And now in this, inside this, you have in the body of this table, you have the constraints coefficients. Minus 2, 1, 1. That is minus 2, 1. You just look at the first constraint. Look at the first constraint. No. Minus 2, 1. Minus 2, 1. Coefficient of S1 is 1. Minus 2, 1, 1. Minus 2, 1, 1. Look at minus 2, 1, 1, 0, 0. Constant, you had 1. And then you had x1 less than or equal to 2. That is x1 plus s1, s2. So x1 coefficient is 1. There is no x2. S1 coefficient is 0. Now S2 coefficient is 1, 0. And the right hand side constant is 2. And the last constant you had 1x1 plus 1x2 plus S3 equal to 3. Okay, right. Now just look at. Now these are right hand side constants, isn't it? Now find out Zj minus Cj. This will always be negative of the constants. Here, these constants, not constraints. The coefficients of x1, x2, etc. These are Cj because Cb, coefficients of basic vectors. These are all Cj's, coefficients of both non-basic and basic vectors. Okay, so it is 0 into minus 2, that is 0 into a1 plus 0 into 1 plus 0 into 1, which will always be 0. Okay, minus your c1 minus 3. So it is minus 2. It is 0, 0, 0. Here similarly, 0 into 1 plus 0 into 2 plus 0 into 3 minus 0 is 0. So this will always be the intersection of the last row and the last column in the starting table will always be 0, and that is the value of your Z, that is Z not equal to 0. Is it right? Okay. Now, what is the next thing? Look forward to the last row. From the last row, the values of Zj minus Ej are all greater than or equal to 0? No. There are negative values. Is it one only? Is it there is only one value or two negative values? There are two negative values. Therefore, of the two negative values, you take the minimum. Minimum by minimum, most negative means minimum value. Minimum of them. So minus 3, minus 2, which is minimum? Minus 3, isn't it? So look at the arrow mark. That shows that column is the pivot column. So the arrow mark indicates, you put an arrow mark that indicates the column that is to be designated as the pivot column. Okay, right. Now we are finding the ratio actually. Okay, we are finding ratio. And here is an arrow mark which shows that particular row is the pivot row. How do you get it? That is the pivot row here, second row. Find out. See, for that, constant divided by the coefficients. And if the coefficient is negative, do not take. Okay. Then here we may have one doubt. 1 by minus 2. Okay. Since it is minus 2, well, we will not take it. Shall we take 1 by 1? Don't go to these two columns. These columns. You should take only those values, those coefficients of A11, A21, A31 under the denominator, in the denominator, because these are the only coefficients that are available in the pivot column. So pivot column elements are only to be considered in the denominator to get the ratio, provided they are positive. So 1 divided by minus 2, do not take. 2 divided by 1 is 2. 3 divided by 1 is 3. So of 2 and 3, the minimum is 2. Therefore, that particular row is called now the pivot row. So which is the pivot element? The element that is at the intersection of pivot column A1 and pivot row, second row, is your pivot element, which here happens to be 1. It may be any number. So in order to make it that pivot element 1, you need to divide it throughout by that number. Suppose it is minus 2, you divide it by minus 2 throughout, as you know very well, throughout that particular row, as in order to make it unity. But here it so happen it is 1. Okay. So whatever I have explained here is now written. So you can just go through now. Most negative Zj minus Cj is minus 3, and hence A1, the first column, is the pivot column. X1 enters the basis. That is very important. So what will happen in the next table only we will be writing. So this is the pivot column. So definitely there is going to be a change. You go to the variable x1, which is in the first column. Since first column is the pivot column, the corresponding non-basic variable, that is the decision variable x1, will enter which row? The second row, because that is found out to be the pivot row now, the second row. So what will happen? S2 will go out and x1 will be enter with its corresponding coefficient 3. We will not put 0 here because 0 is the coefficient of S2. Now, since x1 enters basis and its corresponding coefficient 3 will enter here as the coefficient and S2 will go. Remember, you should not put S2 here. As I already mentioned that it is not swapping. When x1 comes to basic and S2 goes out, not that S2 will become here. S2 will come down to x1 position. No, these will not be, there will not be any change in your original variables and their coefficients. Only which is entering is important. And so naturally what is leaving, of course, naturally it has to go out, but it doesn't come back to its position. It is not a one-to-one correspondent. It is not swapping. It goes out of the picture. That's all. Okay, right. So x1 enters the basis. In the pivot column, the negative element minus 2 should not be taken for finding the ratio. I have explained. The other two ratios are 2 by 1 and 3 by 1. And the minimum ratio is 2 by 1. which corresponds to second row, and hence the second row is the pivot row. Therefore, S2 is the leaving variable because X1 comes to basis as a basic vector. Which place it comes to, whether it replaces S1 or S2 or S3, that is decided by the pivot row, which we have found from the minimum ratio, isn't it? Therefore, here we find that this is the minimum ratio row S2. So S2 will go off and X1 will come to its position. We are very sure because the pivot column element has to enter as a basic variable. But of the three non-basic variable, which is to go off, which is to get out, that is from the corresponding row. Here, pivot row is having corresponding to S2. So S2 will go out. In that place, X1 will come with its corresponding coefficient 3. Okay, right. Now, therefore, S2 is the leaving variable and the pivot element is 1. Since X1 enters the basis, the first column should be transformed into 0, 1, 0. Now, first row, second row, third row. In this, the second row is becoming the pivot row, and already, of course, it has got 1. If it is not 1, you have to make it as 1. It's already 1. Anyway, after making it 1, but in this case, it is already 1. The other two elements of the first column should be made 0 using row operations, elementary row transformation or operation. We make the transformation. What is the new row? R1 dash, which is R1. R1 is nothing but R1 plus 2R2. R1 plus 2R2. What is the meaning? R1 plus 2R2. Here you have minus 2. It should be made 0. R2 you have 1. So R1, new R1 will be R1 existing plus 2 times R2. Minus 2 plus 2, 0. Coming to the next elementary operation, it is this is R3 and this is R2. So it is R3 is R3 minus R2, you get 0. Here it is simple elementary operation, isn't that? So you get, so R1 is R1 plus 2R2 and this changes minus 2 to 0. Also R3 is R3 minus R2, which reduces 1 to 0. The pivot element is 1 and needs no change. The new table is now, look at this. As I already mentioned, X1 has entered into the basic vector position in making S2 leave out. Remember, as I already mentioned, you will not write S2 here. It will not come to the position. It will not replace X1. X1 has come here, therefore S2 will go here. No. These are all standard. These are originally available in your problem. It has to go out. That's all. It is not swapping. It is not exchange. Only non-basic variable whose solution is to be found is now coming into the basic variable picture, replacing, making S2 out. So now write corresponding coefficient 3. These things are already there. This will ever be there. Now, so you have, when you are making this elementary row operation, there is a change here, isn't it? You made this, isn't it? Plus R1 plus 2R2. So naturally here also you have changes 5 to 1. Now over. Go to Zj minus Cj. Okay, you get 0. You get 0 into 0. Don't always write 0. You have to check because when the process is there, when the tables are improving, in fact, the iterations are going on, naturally there will be a change in the values. So you have to be careful. 0 into 0 plus 3 into 1, because now not that all the coefficients are zeros, because X1 has entered here with its coefficient 3. So 3 into 1, 0 plus 3 plus 0, which is 3 minus 3. Zj minus Cj, 0. Similarly, 0 into 1 plus 3 into 0 plus 0 into 1. Of course, 0 minus 2 minus 2. Next is 0. Next here, 0 into 2 plus 3 into 1 plus 0. That is 3 minus 0, 3. Last one, 0. And here, 0 into 5, 0 plus 3 into 2, 6, minus 0, 6. See, there is an improvement in your iteration, so that this last row and column intersection value will be the required maximum value of your given objective function that we are going to visualize and also verify. Okay, now you check the Zj minus Ej, whether all of them are positive. No, there are zeros and positive value, but there is one negative value. Even if there is one negative value, you need to do again, identify a pivot column, identify pivot row, and then do about the same process. You go for one more iteration. Okay, so this second column is now the pivot column. Okay, now you have to find out the pivot row. How to find out? Go for ratio. 5 divided by 1. 5. 2 divided by 0. No. You should not take in the denominator 0 as well as negative value. So the only possibility is 1 divided by 1, which is positive. Therefore, this row is now the pivot row. So you have the pivot row, third row. You have the pivot column, second column. So what will happen? The moment pivot column is identified, you are sure that the corresponding non-basic variable on the top will enter now as a basic variable, where already x1 is there. Will it replace s1 or s3? And that is answered by the pivot row, whether it is first row or third row. That we have found here, it is minimum ratio is obtained at the third row. Therefore, x2 will enter into the basic vector column, where replacing s3. s3 will be out. And when you write x2 here, its corresponding coefficient 2 will appear. And of course, it so happened in this pivot column, being the third row, you have 1. You don't need to make any more simplification. You don't need to have any division for that to make it as unity. It's already 1. But you must ensure that it is 0, 0, 1. Therefore, only one row elementary operation you have to do that. New R1 is R1 minus R3. This is already 0. You don't need to do anything. So 1 minus 1, 0. So correspondingly, this becomes 1. 2 minus of minus 1, 2 plus 1, 3. And 5 minus 1, 4. All those things will be there. Isn't it? Now you are going to see. So here we have thus obtained an improved solution, S1 equal to 5. Where did you get S1 equal to 5? See, S1 equal to 5. Okay. Then x1 equal to 2, s3 equal to 1, z equal to 6, isn't it? So whatever is available in the table, it's shown now. There is one negative Cj bar, which is minus 2. Hence, this solution is not optimal. Which solution is not optimal? x1 equal to 2, s1 equal to 5, s3 equal to 1 are not optimal and can be improved further. That's what I have already explained. The pivot column is the x2 column, because it has got the negative Zj minus Cj. Hence, x2 enters the basis. Taking the ratios 5 by 1, 2 by 0, and 1 by 1, 2 by 0 should not take. We find that the minimum is 1, corresponding to s3 row, that is the third row. Therefore, s3 leaves the basis. And x2 is entering. The pivot column should be changed to, look at, x2 is entering the basic, becoming basic vector, which is corresponding coefficient 2, and s3 out. So now it's already this, you had 1 here, you got 0 here. Operations. Now, having done iterations twice, look at Zj minus Cj. Now, you have 0, 0, 0, 1, 2. So, Zj minus Cj is now greater than or equal to 0. You can have 0 also. And the remaining two are positive. Therefore, you don't need to go for any more iteration. We have reached optimality condition. Optimal solution is reached. Optimal solution is reached. So, what is that optimal solution? Actually, 8. 8 is going to be the maximum value of your Z objective function that is available in your question. And what are the other solutions? By solution, we mean always finding the values of the decision variables in the question in the objective function, so that when you substitute those two, those three, depending upon the nature of the problem, should give you the value of z. But that is readily available in the last row and column intersection. Value itself is the maximum is at 8. And of course, your values of x1, the decision variable is 2, and the decision variable x2 is having the value 1, and s1 equal to 4. So now that table is complete. No more iterations that we have reached optimal solution. The solutions are s1 equal to 4, x1 equal to 2, x2 equal to 1. But remember, the value of S1 or S2 or S3, if they are available in the table, will be of no use to get your value of Z. They just have come and they have been made use of to get the optimality going, and the fine tuning is done. Okay. Now, since there is already 0 as the second element, the x1 row needs no change. So R1 minus R3 already have shown you this reduce 1 to 0. Also, the pivot element itself is 1. The new table is. Okay, so you go see the table. Here all the Z minus Cj are non-negative, and hence the current solution itself is optimal. The optimal solution is, as I just have seen from the table now, S1 equal to 4, X1 equal to 2, X2 equal to 1. Since the coefficient of the slack variable S1 is 0 in the objective function, it need not be taken into account, because in any original objective function, it is only in terms of X1, X2, X3. Isn't that? So slack variables are introduced by S. So they are having coefficients in the original objective function as zeros only. So any improved value for them will not be of any use. But they may appear, they may appear in the table, but they will not be of any use. They will not be of any help to get the value of Z. But you need to only depend on the decision variables values. Okay. Since the coefficient of this, okay, we give the solution in terms of the decision variables x1 and x2 only. Thus, the optimal solution is x1 equal to 2, x2 equal to 1. Z star is nothing but, instead of writing maximum value of Z or max Z, just another notation Z star equal to 8, which you are just able to see at the end of the, at the intersection of the last row and column, gives you straight away. But you must always check. Suppose you have gone wrong in your calculations in the elementary row operations, and if you just look at the last value in the at the intersection and right here, you may sometimes go wrong, provided if the calculation somewhere you have gone wrong. Otherwise, it is better to cross-check. How to cross-check? What was your original function to be maximized, optimized? Z equal to 3x1 plus 2x2. Isn't it? So what is x1 value? 2, 3 into 2, 6. x2 value 1, 2 into 1, 2, 6 plus 2, 8. And that is there in your table also. That means you have done the iterations correctly, and then you have got the optimal solution, which is x1 equal to 2, x2 equal to 1, and max Z equal to 8. Hope you would have understood clearly now how we solved an LPP by simplex method. So we will have a break for about 5 minutes, and then we will resume the class for the next problem. Will they resume the class? I will let me resume the class after 5 minutes break. Okay. And let me resume. Second example, minimize Z is equal to x1 minus 3x2 plus 2x3 subject to the constraints 3x1 minus x2 plus 2x3 less than or equal to 7, minus 2x1 plus 4x2 less than or equal to 12, minus 4x1 plus 3x2 plus 8x3 less than or equal to 10, x1, x2, x3 greater than or equal to 0. So here we have, of course, three decision variables, three constraints, and the last one always indicate the non-negativity of the variables. Now here, but it is a question of finding the minimum value of Z. But then to solve an LPP by simplex method, we should make this in the standard form as a maximization type only. How will you do that? By multiplying throughout by minus sign, you get minus Z equal to minus x1 plus 3x2 minus 2x3. Minus Z, just for brevity, you can just denote it by some other letter, say W. So now finding minimum of Z is the same as finding maximum of minus Z. So that we have made it as a maximization type. So we have to change the problem into maximization type. So take W equal to minus Z so that the problem now becomes maximize W because W is minus Z. So what will be in the right hand side? Minus x1 plus 3x2 minus 2x3. Therefore, the standard form is maximize W. So the entire thing is to be now written in terms of W, isn't it? Maximize W, which is now minus x1 plus 3x2 minus 2x3, subject to the constraints 3x1 minus x2 plus 2x3 plus s1 equal to 7, minus 2x1 plus 4x2 plus s2 equal to 12, minus 4x1 plus 3x2 plus 8x3 plus s3 equal to 10, x1, x2, x3, s1, s2, s3 are all greater than or equal to 0. Just go back. Look at the constraints now. It is now 3x1 minus x2 plus 2x3 plus s1 equal to 7. Next is minus 2x1 plus 4x2 plus s2 equal to 12. Minus 4x1 plus 3x2 plus 8x3 plus s3 equal to 10. So there are no changes in the constraints because you have only the constraints are of less than or equal to type. If they are of greater than or equal to type, then you have to make it as less than or equal to type. Then you have to add only slack variables. Okay. But now that all the three constraints are having less than or equal to type, are of less than or equal to type, therefore you just have to add slack variables S1, S2, S3 in that order. Of course, x1, x2, x3, s1, s2, s3 greater than or equal to 0. So we will start with the table called the initial table. As we have just seen in the first problem, you have Z common, that is equal to objective function. But this is given, actually better it is better you write the variables in the first row and the coefficients in the second row. That will be better because you are writing, this is the row where you have CB, that is coefficients for basic vectors. Okay. Therefore, the same way you can write the coefficients here and you can write the variables here. Nothing wrong in writing it this way, but that will be more appropriate. So you can write in the first row as in the first problem, x1, x2, x3, s1, s2, s3. The coefficients you write now. Okay. So what is the coefficients? Minus 1, 3, minus 2, 0, 0, 0. Look at it is now maximization of W And this problem is now minus x1 plus 3x2 minus 2x3. Isn't it? Therefore, here there is a mistake, which of course could not be edited. This is already copy pasted. So it should be W. Okay, this should be W. So it is not Z now. It is no longer Z in this problem hereafter. Because finally, of course, we are going to find a minimum Z, what is asked in the question, but we have changed it to maximization of W. Therefore, it is not Z here, it should be W. Okay, as before, coefficients of the constraints of x1, x2, x3, s1, s2, s3, 3 minus 1, 2, 1, 0, 0, minus 2, 4, 0, 0, 1, 0, minus 4, 3, 8, 0, 0, 1. So as I mentioned in the very beginning in simplex algorithm, that the coefficients of s1, s2, s3 in the constraints will form a unit matrix. Okay, right. So here, of course, you will write basic vectors s1, s2, s3, that coefficients always 0, 0, 0 initially. And here the constant also 0. Constant you will write here, you will put 0 here. And of course, it is better. It was not shown in the first problem, one more column of writing, giving the title ratio. It's better. There it was shown outside the table, outside the last column ratio. But it's better you write with the title ratio and show the calculation. That would be nice. Okay, right. Self-explanatory. So now, as usual, go for finding Zj minus Ej. So it is 0 into 3 plus 0 into minus 2 plus 0 into minus 4. So in the initial table, it will only be negative of your coefficients. Don't say it is minus 1, minus 2, minus 3 only. As this I have cautioned already in the beginning itself. If the coefficients are positive, you will definitely have negative because it is 0 minus. If the coefficients you can also have minus, then it will become minus of minus. So it is minus of minus 1, so plus 1, 0 minus 3, 0 minus of minus 2 plus 2, 0, 0, 0. This is 0 minus 0, 0. Okay. Now, you look forward to the values of Zj minus Cj, whether all are greater than or equal to 0. Then you don't need to go for any iteration. That whatever you have, that will be the optimal solution. But remember, you have one negative value. If there is more than one negative value, you have to take the minimum of the minimum of the values that you have seen in the previous problem, isn't it? So here there is only one negative value. So that value refers to the column as the pivot column. So what is the pivot column then? Second column, isn't it? That is the column corresponding to the variable x2, which means that x2 will enter into the basis. In the sense, this non-basic vector x2 will become a basic vector, which means it should replace S1 or S2 or S3. That is, it has to go to first row or second row or third row, which is going to be identified as pivot row. Which is pivot row? For that, you need to go to ratio finding. Constant divided by the elements of the non-negative, the positive, only positive elements in the denominator. The ratio of the constant is the positive elements of the pivot column only. So 7 by minus 1, ignore. 12 by 4, 3. 10 by 3, 3 point something. 10 by 3 is 3.33, isn't it? 10, 9, 1, you get 0, then 3, 10.0, 3.03, etc. So anyway, of these two, this is the minimum. So that corresponds to the second row. This is first row, this is second row, this is third row. So that's why we put an arrow mark to indicate clearly which row is your pivot row. So at the intersection of the pivot row, second row, and the pivot column, second column in this problem, you have an element that is your pivot element. Okay, fine. And the pivot element identification itself shows you that the non-basic variable that enters as a basic variable, that becomes as a basic variable, is a x2 with its corresponding coefficient 3. Okay, in the next iteration table. So What will happen now? You must also do, first you should make the pivot element to be unity, which is possible when you divide throughout by 4. So you get correspondingly, you are going to divide throughout this row, this row throughout by 4. Okay, not the ratio. The ratio don't consider. It is only to find the pivot ratio, pivot row that is over now. You have to have only up to this table, isn't it? Okay, right. So next you have to think of this after making this as 1, or you can do it even simultaneously. So with this as 1, you what you have to do now? So see R2 dash, that is new row, second row is your R2 by 4, that is divided by 4. Okay. Now what is new R1 dash, new row 1 R1, this minus 1 plus 1 by 4th of this R2. 1 by 4 into 4, it's 1 minus 1 plus 1, 0. Similarly, this 3 must be made 0. So R3 minus 3 by 4 into R2. So you will get here 0, 1, 0. Correspondingly, we will have changes in your other elements also. That is done by row elementary operations or elementary row operations. So what's happening now? Of course, you must keep other entries are also available here. First iteration, you should not just write only the values so that you will miss the sequence. So here, what I said, from the second row in that first table, x2 enters the pivot ratio second row with its corresponding coefficient 3, and you had made it divided by 4 1, so minus 1 by 2, it is 1 by 4, 12 by 4 3, etc. Similarly, you have made other calculations. Now you go for Zj minus Ej. It is now 0 into 5 by 2 plus 3 into minus 1 by 2 minus 3 by 2 plus you had in the beginning minus 3 by 2 minus or minus 1, minus 3 by 2 plus 1, that is you had minus half, isn't that? So it you have minus half. Similarly, you have to make all elements by making the corresponding this one. So you are making now minus half, you are having here 0, here 2, etc. Now Zj minus Ej is still having a negative value. That means the solution that you have obtained is not optimal. You need to go for further iteration. So identify the pivot column. So there is only one negative value, that is the first column. Therefore, this is the pivot column. Now go for find. So pivot column itself shows that the next entering non-basic variable to basic is x1, because this is the first column with its corresponding coefficient. Okay. Then you have to go for finding pivot row. For that, you go to the constant, divide the constant by positive coefficient in the first column. 10 by 5 by 2, that is 10 into 2 by 5, 4. Then 3 by negative value, don't consider. 1 divided by negative value, don't consider. Therefore, the only positive value as the ratio, there is no need to compare. Automatically says that first row is the pivot row. That means your x1 non-basic variable will enter your basis replacing S1 in the first row with its corresponding coefficient. Okay. And not only that, now you have to make this 5 by 2 is your pivot element, which is at the intersection of your first row and the first column. So what is your R1 dash, that is new R1 into 2 by 5. That is 5 by 2 into 2 by 5, it is made 1. Similarly, you find out this makes 0, this is to be also made 0. So new R2 is R2 existing R2 plus R1 by 5. Similarly, R3 dash is R3 plus R1. So all these things you do minus 5 by 2 plus 5 by 2, 0. So that the new table now, second iteration. Table is now, these are all fixed. But now already x2 has entered in the first iteration with its coefficient 3. Now in the second iteration, you have seen from the first column corresponding variable x1 with its corresponding coefficient minus 1 as the basic variable. S1 is out. Already S2 was also out. Okay, so we will still find the SHJ minus CJ. Minus 1 plus 0 plus 0, minus of minus 1. So you go minus 1, minus of minus 1, minus 1, 0. Then 0 plus 3, minus 3, 0. Next, minus 4 by 5 plus 6 by 5. You get minus 4 by 5 plus 6 by 5. That is 2 by 5 minus of minus 2. Isn't that? So it is 12 by 5. Next is minus 2 by 5 plus 3 by 5. So 1 by 5 minus 0, you get 1 by 5. Minus 1 by 10 plus 9 by 10. So 8 by 10. That is 4 by 5 minus 0, 4 by 5. The last one 0, 0, 0 minus 0, 0. And this minus 4 plus 15 plus 0. That is 11 minus 0, 11. That's all. Okay. Now check for ZJ minus CJ values. Are you having all of them to be greater than or equal to 0? Yes. 0, 0, positive, 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 0. That means optimality is reached. Optimal solution has been obtained. No more iteration is required. So with these 2 iterations, we have come to the stage of getting the optimal solution. For that, where are you getting the solutions for your variables? From the basic variables column, this vector x1, x2. Of course, you may have slack variables also and the corresponding values also. You can write down, nothing wrong, but that will not be of any help to find out your maximum or minimum value of the objective function Z. Okay, right. Since Zj minus Ej are all greater than or equal to 0 for all j, optimal solution is obtained given by x1 equal to 4. The last column constant is the value. x2 is equal to 5 and s3 is equal to 11. You may write s3 equal to 11 or sometimes you don't need to. You don't need to. It is not mandatory. Only the variables that are decision variables you need to identify and write. Okay. So all Zj minus Cj greater than or equal to 0. Thus the optimal solution is reached. Thus the optimal solution is x1 equal to 4, x2 equal to 5. Well, x3 was there in the original objective function, which is not there in your basic vector column. So you have to put 0. Isn't that? x3 equal to 0. Well, you have x3 value 11, but that is of no help. But x3 is needed, which is not found in your basic vector column. Therefore, put x3 equal to 0. Okay. Now, W star. Star just stands for writing max or min, depending upon, of course, but in simplex method, it is only maximum. Okay. Because if it is really maximum given originally, it is maximum. If it is also made to be maximum only. So it is for the W function, max W, that is W star equal to, just look back. You have, as I said, in the last row, last column, under constant, you have the intersection value. That is the required value, maximum value of the objective function. 11. Okay. 11. That's all. But then, this 11 first let us verify. Okay. Now, what is your original problem? Max W is minus x1 plus 3x2 minus 2x3. x3 is 0. So it goes off. Isn't it? So here you have minus x1. x1 value 4. x2 value 5. So minus 4 plus 15, you get 11. So the calculations found out after the second iteration showing you W star, that is maximum W equal to 11, is correct. But remember, W is just that we have introduced in place of minus Z. Isn't it? Because finding maximum W is the same as minimum of minimum. See, W is actually minus Z, isn't it? So minimum of Z is your maximum of W, where W equal to minus Z. Therefore, what is your Z? When W, that is here, Z star is actually minimum Z. In your problem, it is minimize Z. So you can put, say here, you may ask one doubt. So we have put 0 star here for maximization or maximum value of W. Here we are putting star again to denote minimum of Z. Nothing wrong in it. Suppose if you feel that it is not appropriate, or if you are not comfortable, you can simply still write minimum z equal to. Okay, so w equal to maximum value of w is 11, w equal to minus z, therefore z is minus 11, and that is the minimum value of z. That is the minimum value of z. Okay, so you can straight away write the solution of the given LPPV is x1 equal to 4, x2 equal to 5, x3 equal to 0, and minimum z equal to minus 11. The solution. Well, already we have seen in detail a standard form, a standard problem. Just a minute. Called a ready mix problem. We had used it in showing as an example to solve by graphical method, and now that we are again taking up the same problem to solve by simplex method. Okay, you can even compare the results. You will be getting the same. You should be. We use the ready mix model to explain the details of the simplex method. The problem is expressed in equation form as maximize z equal to 5x1 plus 4x2 plus 0s1 plus 0s2 plus 0s3 plus 0s4. Subject to the constraints 6x1 plus 4x2 plus s1 equal to 24, x1 plus 2x2 plus s2 equal to 6, minus x1 plus x2 plus s3 equal to 1, x2 plus s4 equal to 2. So here are, remember, only two decision variables in the original problem, but then there are 4 constraints. So there is no connection between the number of constraints and the number of variables. Okay, it is not necessary that they should match. The variables s1, s2, s3, and s4 are the slacks associated with the respective constraints. We write the objective function as, well, this can also be written this way. This is also just another method of rewriting the objective function as z minus of, or whatever the coefficients that are available on the left hand side to becoming to right hand side, instead of taking into account the slack variables, just straight away the problem like maximum z equal 5x1 plus 4x2 becomes z minus 5x1 minus 4x2 equal to 0. In this manner, the starting simplex tableau can be represented as follows. So this is just another way of writing. It's also almost the same idea. Same idea. Everything is there. You have x1, x2, s1, s2, s3, s4. You have, since you are taking everything into the right hand side equal to 0, you are writing, it is written here 0. Otherwise, also constant, you can write 0 only. We have by solution here, actually, we write there as a constant. Here it is written straight away the solution. Fine. That's also okay. Fine. Okay. So you have those constants here. Basically, you have s1, s2, s3, 4 coefficient zeros, and then these are x1, x2 coefficient. These are our slack variables coefficient. Then you have inside the constraints coefficient. The same way, but slight change. And row wise, you will be finding this is s1 row, s2 row, s3 row, s4 row. This is z row. Well, that's just an identification. Okay, right. The same thing is there. So basically, when x1, x2 equals 0, 0, z value is 0, and s1 is 24, s2 is 6, s3 is 1, s4 is 4, S4 is 2, is called the initialization or initial simplex table. Then the same thing. This information is shown in the table by listing the basic variables in the leftmost basic column and their values in the rightmost solution column, the constants. In effect, the tabular defines the current corner point by specifying its basic variables and their values as well as the corresponding value of the objective function. Remember that the non-basic variable, those not listed in the basic column, always equal 0. That is, they are on the top. They are actually the decision variables. Non-basic variables are the decision variables, x1, x2, etc. Okay, like that. The same thing is there. The conditions are known given here. The same thing we have done. Ratio 6/1. This is 1 by -1 ignore because negative value we don't need to take. Again by 0 also it becomes infinity. That is also to be ignored. So there is only one ratio which is eligible. So that is the pivot row. And of course, Zj minus Cj calculations are not shown here straight away. First, what is to be, which non-basic variable enters and which basic variable leaves is shown here. And then we just find out the pivot column, pivot row as before. It is now, so the pivot column is there. Okay, x1 is entering. And this is pivot row. Just now we have seen the first row. This is just another way of calculating. The computations are applied to the preceding table in the following manner. Replace S1 in the basic column with a x1, and new x1 row is current s1 row divided by 6. The same way that it is done with slight changes. And well, I think I would suggest instead of just writing the coefficients in as a row and then making some minus, the same thing is taking place. But if you take it up the way that it was shown in the first two problems as a table and do the elementary row operations there itself, it will be easy for you to understand than this type of going for row-wise computations. Idea is the same. You will get the same type of solution, same computations, but the way that you do it will slightly be cumbersome. Okay, otherwise you get the same. Okay, so after the second iteration, you have the 6 by you have 6, 1.5, 3, 2, the ratio. 1.5 is the minimum. So entering x2, okay, the same thing. It is shown again how to get the new x2 row, current s2 row, which is leaving, and divided by the its coefficient. All these things are there. Okay, same thing. So now that you are having, so we have already calculated, which is not shown here as I have done it in the previous problems. Sj minus Cj. Instead, it is straight away showing you here, based on the optimality condition, none of the zero row, Z row coefficients associated with the non-basic variable are negative. Again, the table, last table is the optimal. Instead, you can better go for that way of finding Zj minus Cj. The same thing is done, greater than or equal to 0, non-negative. Okay, with the same thing. You have Z value at the last value. Here it is shown in the first row. All other values are there for you for your x1, x2, s3, s4. Okay. So we are interested only in the values of variables x1 and x2 and the corresponding value of z, which is maximum as 21. So you have 3 by 2, 21 is the solution. Okay. So answer, the optimum solution can be read from the simplex table itself. So the optimal values of the variables in the basic column are given in the right-hand side solution column and can be interpreted as now decision variable x1, optimum value 3. So it's a recommendation. Well, we are just reproducing as a phrase. Produce 3 tons of exterior paint daily according to the problem. x2, that is a recommendation. Decision variable x2 value 3 by 2. Produce 1.5 tons of interior paint daily. And z, the objective function. Optimum value we have seen 21. Daily profit is 20. The profit is given in thousands of dollars. So $21,000. Okay. So you can verify that the values S3 equal to S1 equal to 0, S2 equal to 0, S3 equal to 5 by 2, S4 equal to 1 by 2 are consistent with the given values. Okay, anyway, let us not bother about these S1 values, S1, S2, S3, S4, but you have to check whether your 21 is correct for your are commensurate with the values of your decision variables. 3 by 2, 21, isn't that? So let's go back to the problem. Five x1, 5 into 3, 15 plus x2, 1.5, 4 into 1.5, 6, 15 plus 6, 21. And that was shown in the simplex table itself as the last value. Okay, so Z value 21. So maximum value of Z is 21 when x1 equal to 3, x2 equal to 1.5 is correct. So thus we just make a summary of what we have seen so far. As far we have dealt with the maximization case, and also we have seen an example of minimization. Okay, so it is just maximum of the, it has to be made to be of maximization type by changing the variable into its negative and go for maximization problem. Okay. So this follows maximum Z is equal to minimum of minus Z. Okay. As for the feasibility condition for selecting the living variable, all the things, rules remain unchanged. We've already seen optimality condition, feasibility condition. So the entering variable in a maximization okay. So we have seen most of the negative value we are taking as the pivot column. Then we go for finding the ratios of the constant with the positive elements of your pivot column, and we take the minimum ratio as the pivot row, intersecting element as a pivot element. We make it unity, other elements 0 by elementary row operations, and so on. Yeah, thus the steps involved in the simplex method are summarized as below. Step 1, determine a starting basic feasible solution. Step 2, select an entering variable using the optimality condition. Stop if there is no entering variable. The last solution is optimal. Better, I would suggest that if Zj minus Cj greater than or equal to 0 for all j, then optimality condition is reached. So that is the optimal solution. You don't need to go for any more iteration. Okay. Otherwise, go to the next step. That is, you improve upon value of Z by taking the most of the negative, or if there is only one negative, that is the pivot column, and so on. Okay. Exercises. So the moment you reached a stage where after one iteration or two iterations or third iteration, as the case may be, if you ensure that Zj minus Cj is greater than or equal to 0 for all j, you have reached optimum condition. That is, optimal solution is obtained. So you have to identify those of the basic variables, that is non-basic variables entered into basic basis, and have their corresponding values in the constant column. And of course, you may have slack variables also to have some values, but you don't need to worry. You don't need to write them about, and take only those values of decision variables and check with the objective function that is originally given. And also, of course, that is readily available at the intersection of the last row and the last column in the simplex table itself after required number of iterations are done with the optimality is obtained. So with this background, we may go for solving exercises. Solving the following LPP by simplex method. Max Z equal to, that is maximize the objective function Z equal to 3x1 plus 2x2. Subject to the constraints x1 plus x2 less than or equal to 4, x1 minus x2 less than or equal to 2, and x1 comma x2 greater than or equal to 0. Solve the following LPP by simplex method. Maximize Z equal to 6x1 plus 9x2. subject to the constraints 2x1 plus 2x2 less than or equal to 24, x1 plus 5x2 less than or equal to 44, 6x1 plus 2x2 less than or equal to 60, and of course non-negativity of the decision variables x1, x2 greater than or equal to 0. Well, so this is what all about solving an LPP using simplex method. If you got any doubt, you may seek clarification. You may get it clarified. If there are doubts, hope all of you have understood. Any other feedback? Anything else you want to know, anyone? Well, if you don't have any more queries or any doubts to be clarified, then I stop sharing.